versus pairwise.
Hello.
Definitions.
Hello. Ok, ya mierda.
We'll have a look at a fun problem and then we'll solve that. So just very first thing, if you've got a collection of events, maybe you've got events A, B, and C, they're pairwise independent if each pair basically are independent. So A and B are independent, B and C are independent, and A and C are also independent. And then a slightly stronger condition is rather than just being pairwise independent, they could also be mutually independent.
¿Qué tal si te callas, huevón?
Definitions.
Mentira,
and then we'll have
amigo.
a fun problem, and then we'll solve that. So just very first thing, if you've got a collection of events, maybe you've got events A, B, and C, they're pairwise independent if each pair basically are independent. So A and B are independent, B and C are independent, and A and C are also independent.
Right.
And then a slightly stronger condition is rather than just being pairwise independent, they could also be mutually independent.
Okay.
If the probability of all three happening is the same as the product of the three probabilities.
Mutually independent.
And more generally, if you had just a general collection of events, they're mutually independent if for any subset of events, basically the subset behave like this, that they're independent. And you can come up with lots of nice sort of simple examples to demonstrate that it's possible to have basically pairwise independent events that aren't mutually independent. So we'll just go with an example I've picked here where you've got, basically you're picking uniformly at random from the numbers 1, 2, 3, and 4, and your events A, B, and C are these pairs of numbers. And you can quite easily check that the probability of all of these is a half, and then if you look at the probability of A and B, this is basically the probability of just picking the number 2. So this is a quarter, and then you see if you multiply the probability of A and the probability of B, you get a quarter as well. So that means that A and B are independent, and just by symmetry you can do the same thing to show that B and C and also A and C are independent. So
Okay.
A, B, and C here, these are all pairwise independent.
Doesn't
However,
mean...
if we now look at the probability of all three of them happening, well, the intersection of A, B, and C is actually just empty. There's no number that's in all three of those.
Right.
So the probability of all three of them happening is 0. So this isn't equal to a half times.
So they're not mutually collective, mutually independent. I mean, yeah, they're not mutually independent, but they are
Let's have three events, A, B, and C, which are pairwise independent. So A and B aren't independent. 0. C is pairwise independent, and just by symmetry you can do the same thing to show that B and C and also A and C are independent. So A, B, and C here, these are all pairwise independent. However, if we now look at the probability of all three of them happening, well, the intersection of A, B, and C is actually just empty. There's no number that's in all three. Of those. So the probability of all three of them happening is 0. So this isn't equal to a half times a half times a half. So we've got three events here which are not mutually independent. So there you go. It's possible to have three events, A, B, and C, which are pairwise independent, but they're not mutually independent because the probability of all three of them happening kind of lets you down and doesn't satisfy this rule. And I was thinking about this recently, and I was thinking, what if you try and have some events which are pairwise not independent? So A and B aren't independent, B and C aren't, A and C aren't. But then is it still possible to have that as a trio they kind of behave independently? So just a warning, this wouldn't mean that they're mutually independent but not pairwise independent, because mutually
what if for my coat, what if for my blunt, what if for my coat, what if for my blunt, what if for my blunt? Verga.
independent needs them to be pairwise independent.
A ver, concha de tu madre, no estoy entendiendo.
Doesn't
Cosita.
satisfy this rule.
No mutual independent, claro, porque no son. No todos tienen una intersección entre todos.
And I was thinking
Pero estos, sí, entre todos. A ver, puta, no sé cómo explicarlo, pero si uno con el otro, pero solo uno con otro. Fuck you, nigga. Son, independent or equal. They're independent. They're pairwise independent, but they're not mutual independent
about
because not all of the integrantes, not all of the elements are. Fuck you. Not all the groups have the same element,
this recently, and I was thinking, what if you try and have some events which are pairwise not
But-
independent? So A and B are
independent, but they are
independent.
mutually
and then
independent.
B and C aren't, A and C aren't.
Is that
But
possible?
then is
No.
it still possible to have
Yo, not at all, not at all. I don't think so. No, impossible. Impossible. No, impossible. Impossible.
that as a trio they kind of behave independently? So just a warning, this wouldn't mean that they're mutually independent but not pairwise independent, because mutually independent needs them to be pairwise independent as well.
Exactly.
This is just sort of a little curiosity here I was wondering about. So if you're interested in trying to come up with your own examples, do pause the video here, have a think about this, otherwise I'll go into sharing my solution.
Sure, what? Oh, okay.
So actually I found lots of different solutions to this. It turns out there's a lot of freedom and flexibility over what your probabilities can be.
Oh, you
So
want me
let's
to
just
do a proof?
Get a diagram here so we can try and label all the different
Come on. Okay, Okay, so si estos weones pues no son pairwise, o sea, no hay aquí nada. Fuck you. Oh, shit. I mean, si no hay, a ver, si no hay acá nada, no es solo esto.
probabilities
Es todo esto.
diagram.
En serio se puede hacer clic así. Es todo esto. Esto es A and B. Todo esto. O sea, no hay nada. Pero depende por ejemplo, si es exclusive or, I mean, pero claro, tendría que ser como que A, B, and C intersect, but A and B, they don't intersect. So this is empty. A and C doesn't intersect, empty. B and C doesn't intersect, B. However, all of them intersect at C. I mean at A, B, C. I don't know how to write this though.
And basically, I'll talk you through my first approach here, which was I thought I'd try just making some assumptions, see where it took me. So I assumed, let's say that the probability of A, B, and C, these all have probability at half. And then we're looking for the probability of the intersection to be a half to the power of 3, so an eighth. And then we could label that eighth on the diagram immediately, which is nice. And then next I figured that, well, we might have some flexibility. All the probabilities are going to have to satisfy the inclusion-exclusion principle for 3 different events. So the probability of the union of all 3, this has to be equal to the sum of the
Shut the matter. Ah! Concéntrate.
All the probabilities
Focus.
are going to have to
Yeah, what the fuck you doing, brody? The 7 millennial problems play in 7 minutes. Te lo resuelvo ahorita, weón. Con un huevo te lo resuelvo, man.
satisfy the inclusion-exclusion principle.
Okay, exclusion. Yeah, that's what I'm talking about.
Probability. All the probabilities are going to have to satisfy the inclusion-exclusion principle for 3 different events. So the probability of the union of all 3, this has to be equal to the sum of the probabilities. Take away the pairwise intersections and then
Minus.
add the intersection of all 3 of them. So this is just sort of a standard result from set theory here being applied to probability. And then we know the probability of A, the probability of B, probability of C, and the probability of the intersection of all 3. So this gives us a half plus a half plus a half. The
Right. 3 halves.
We've also got a plus an eighth there, so we'll add these together, deal with those later. And then next thing I did here was I thought, okay, well, let's just try the probability of A union B union C is equal to 1.
It's equal to 1.
So that gives us 1 equals to all of this stuff on the right-hand side.
Yeah.
And on the diagram there, we can fill in a 0 then if we're saying the union of all three is actually got probability 1. And then what we can do is we can rearrange our equation here. You'll find that 5/8 then is equal to the sum of the probabilities of these intersections. And then what we could do next is, if we want it to be nice...
Why 5 though? Oh, because we subtract, right? So we have 6, 8, 7, 8. Wait, why, bro? Why the fuck? 6 over 8. No, my bad. 12, 13 over 8. Oh, minus 8.
and symmetrical, so ideally we'll find a nice elegant solution. Let's say that these three probabilities are all equal. So then you're looking for a probability of 5.
Why would they be equal though? Why? It's impossible though, right?
24ths for the probability of A and B. And you've already got 3 24ths in the very centre there, so you just add in another 2 24ths or 1 12th.
Listen to yeah when he says shit.
There, and then do the same for each of those.
Wait. You gotta tell me, where the fuck you get that 1/12th?
24th.
I don't know.
So then you're looking for a probability of 5 24ths for...
Why, brother? 5/24. Oh, because I don't know.
And then what we can do is we can rearrange our equation here. You'll find that 5/8 then is equal to the sum of the probabilities of these intersections.
Intersections. They are just intersection. Blah, 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 blah. Right.
And then what we could do next is, if we want it to be nice and symmetrical, so ideally we'll find a nice elegant solution. Let's say that these
1/2 times 1/2.
three probabilities are all equal. So then you're looking for a probability of 5 24.
They're all equal. Why? 5/24. Wait, what? 5/24. Oh no, I don't. What the fuck? I don't get it. Don't get it. Oh shit.
For the probability of A and B. And you've already got 3 24ths in the
3 24ths.
very centre there, so you just add in another 2 24ths. Or 1 12th there, and then do the same for each of those. So now 24ths or
Come on, bro.
1 12th there, and then do the same for each of those.
Wait, now I don't fucking get this. Come on.
Probability of A and B. Ideally we'll find a nice elegant solution. Let's say that these three probabilities are all equal. So then you're looking for a probability of 5 24ths for
5/24ths.
the probability of A and B.
Only A and B?
And you've already got
I don't get this, bro.
3/24 in the very center there, so you just add in
3/24? Oh, yeah, here. Oh. Interesting.
another 2/24 or
2/24. This is two. Okay, the 2/24. So you're telling me all this to 5/24?
1/12 there, and then do the same for each of those.
Right.
So now we've kind of filled in so that the probability of A and B, the probability of B and C, the probability of A and C, these are all 5/24. So
5/24. So this should be 2/24. What the fuck? hold on. 2/24, 5/24. So only this is 5/24. What? So is this empty? Or what?
we add those, that gives us our 5/8. So we are satisfying the inclusion-exclusion principle here. And then this is really nice because now we know that we want the probability of A to be a half, probability of B, probability of C, these need to be a half. And then we can just fill in the remaining numbers, which, if you do the calculation with the fraction,
Oh shit. Hold on. 2/24, 3/24, 5/24. I don't get this. 6/24. If we add it all together, that's only, oh no, 4. I mean, yeah, 5, 6/24. How the fuck 6/24 is 1/2? You know what I mean? Okay, my bad. This is 3 plus 5 plus 2 plus 2, which is 7 plus 1, which is 8/24. That's 1/3 though. Then it
you get 1/24. So there you go, we've got another example then, where if we check this really carefully now, the probability of A and the probability of B, the probability of C, these are all a half, but the probability of A and B, the probability of B and C, the probability of A and C, these are all 5/24. So when you multiply your two probabilities, you get a quarter, but this isn't equal to the 5/24. So
yeah, it's not.
these are pairwise, not independent, so none of the pairs are independent. The probability of B and C, the probability of A and C, these are all 5/24. So when you multiply your two probabilities, you get a quarter, but this isn't equal to the 5/24. So these are pairwise, not independent, so none of the pairs are independent. So this means that we've satisfied our first condition, that pairwise they're all not independent of each other. So A and B aren't independent, B and C aren't independent, A and C aren't independent.
Yeah.
And remember, we set this up specifically so that the probability of A and B and C was going to be 1/8, which is a half times a half times a half, or the product of the probabilities of A, B, and C. So this is fantastic. We've actually managed to show that there is such an example out there of this kind of, it's not quite mutually independent or pairwise independent, it's just sort of satisfying this fun kind of property we've been looking at. But unfortunately, I wasn't actually too satisfied with this example, because when I tried to think of a nice way of explaining this, perhaps in terms of some sort of real-life scenario or a game to play,
Right.
I couldn't think of anything too sort of simple or concrete that would make sense for these particular probabilities. I mean, do let me know if you think of anything yourself. I'd be interested to hear. But fortunately, I was able to think of some other examples. So I've got quite a nice one coming up where it does have quite a nice sort of scenario attached to it that hopefully feels kind of intuitive. So anyway, moving on, I did manage to find a few more nice symmetrical examples like this one. So here you can check that they're not pairwise independent, but then the probability of A, B, and C happening is an eighth, and the probability of each of A, B, or C, these all have probability a half, so it does satisfy this extra kind of condition. And this example here, I'm particularly pleased, does satisfy this
5, 8.
extra kind of condition. And this example here I'm particularly pleased with. So this is the one where I've managed to find a situation that kind of goes with this. So we'll just really quickly sort of check the numbers here. You can see that the probability of A, B, and C
Right.
have probability a third. You can see that the probability of A and B happening is a 27th, which is no good, because if you do the probability of A times probability of B, you get a ninth. This isn't equal to it, so A and B aren't independent. And similarly, B and C aren't independent, and A and C aren't independent. And then if you want to check as well, the probability of the intersection of all three is 1/27th. But then this is equal to a third times a third times a third. And this is equal to the probability of A times the probability of B times the probability of C. So this does satisfy our kind of condition that we're interested in here. Now, what's the real life scenario that goes with this example? Well, imagine you've got this very unlucky looking dartboard here, split up into 13 regions, each of these is split into 2, and you've also got a bullseye in the middle, so a total of 27 regions. If you imagine somebody throws a dart at this and they've got an equal chance of hitting any of the 27 regions, well, let's say that player A wins if this person hits any of the numbers between 1 and 4, or if they hit the bull. Say that player B wins if you get 5 to 6 or the bull, and player C wins if you get 9 to 12 or the bull. And nobody wins if you hit 13. So you can see here quite easily that the probability of A, B, and C all winning is just the probability of hitting the bull, which is 1 in 27. And you can see the probability of A winning is a third, the probability of B winning is a third, probability of C winning is a third. So it does sort of behave as a trio, A, B, and C, like they're independent, which is what we were looking for. The probability of A times probability of B times probability of C is equal to the probability of the intersection of all three. But then you can check that each pair, A and B, B and C, A and C, none of these are independent of each other, just as we were looking for.
Okay. Wow. It is fucking speed. Wow. Nada. Bueno. Venga para ti, ¿no? Independent roles from affairs. Fuck you. God damn. Media hora más, hermanito. Media hora más. Let's go. to rule this line. Why not? Oh yeah, wait. Oh yeah, because when I have them intersection, we only have 3. Okay, sure. 4 out of 36. 4 out of 36. Good. So they are not pairwise, but they are mutually independent? Is that what you're telling me, bro? No, here we have. Right. Está bien caliente la mierda, A la puta madre. Voy a cerrar esta hueva, bonito. Lo cierro y a la pinga, ¿sí o no? ¿Yo qué pues? Esta va también. Mario, qué mierda. There we go. ¿Instalar qué? Buenazo. Que caga, es mucho RAM, mucho RAM. Te que lo eyaculo con RAM, weón. Te lo fornico. Es puro ramsazo. Ramses Menezes. Ok, shut up. Complement. Reliability. Interesting. Prepare. PIG. Huh. I mean J. In which all links are up. I don't know, B? Because probably the link is up. Okay, which is pretty high. Series and parallel connections of 3 components in a reliability problem. Dynamic programming, wow. Probability programming. Isn't that cool? Purdue. What? What are you talking about? Never reliability. Wow. Engineering presentations. Wow.
Independence is a very useful property.
The same guy? Oh, the same fucking guy. Huh. Entertaining. I mean, yeah. Cloud Fable.
Last week, Anthropic stood on the global stage.
Yeah, I want to watch this video. Sounds so interesting. It looks so interesting.
When you think about IQ, you might think about...
Yeah, I'm a fucking genius and you are a fucking stupid ass bitch. So I'm a genius and you're a fucking black nigga. Yeah. Cuidado. Subsystems. Okay, let's do this. A secret third fact. I really know. Wow. Students is exactly 8 years old. Okay. What the fuck do you mean? What was dependent? What? What the fuck was dependent? What? Good. Intersection, multiplication, yeah. And for 2 events. Only 2 events? No, a lot of events. Yeah, AI events. Belong to S. Exact same time. P, man. Yeah. But only the intersection though. Hmm. $1.15. Where is 1.15? Like this. Stop succeeds. Demonstrates subsystem succeeds needed for balance components are out. Components. Yeah. I mean, this is like conditional probability, right? Oh. But why have many ones when only big single one? If any. Thanks. I read this shit, bro. X approaching Y or what? Okay. What is this? PC, PV, PV. Oh, okay. PV, okay. PC, PF. To multiply these motherfuckers. Yeah. Only one, right? No. Not necessarily, but okay. What the fuck? I think that's a really bad example. What? Wow. Most horrible. Most wrinkles aren't real. Hmm. Hmm. Right. Wow. It's so crazy. Wow. All these parallel systems. Cool. This is series systems. What is this? Should be series. This is the exact formula I'm questioning. So it goes up. Wow. Cheap parts. Oh, this is in parallel. Oh, I see. Yeah. Right. ¿Qué carajo quieres? Give me 3 minutes, right? Sigue caliente, ya no tanto. Bueno, sigue caliente, pero ya no tanto. Chambas. Bernoulli trials.
Whenever it is true, we can
I love what he say. Whenever, when. Doesn't mean. Engineering mathematics. Cool. Oh, looks like something.
Answering. Hey everyone, welcome to Happen. Could easily represent the x, and then we could score a fail. Total number of ways called a.
What the fuck? Is that water? No fucking way.
What is-
That's so cool. Whatever that was so fucking cool. Okay, I don't get this part. What is that? Okay, todo por hoy. Todo por hoy, guapuritas. Y ya, pues, ya.